Have you ever stopped to really look up at the night sky and let the sheer scale of it all sink in? Those countless stars, galaxies stretching farther than our minds can grasp, and the quiet, rhythmic dance of planets moving with impossible precision. It feels almost too perfect to be random. And that's the mystery we're diving into today. Why does the universe work like a finely tuned machine, where even the slightest change in gravity or the strength of atomic bonds would make life impossible? It's as if every law of physics, every constant in nature, was carefully calibrated just to allow us to exist. Think about it. The universe isn't just haphazardly holding itself together. The speed of light, the force of gravity, the way particles interact, these aren't arbitrary numbers. They're precise, almost meticulously chosen values that create the perfect conditions for planets to form, for stars to shine, and for life to emerge. If any one of these constants were off by even a fraction, the cosmos as we know it would collapse into chaos. So how did we get so lucky? Is this perfection just a cosmic coincidence, or is there something deeper at play, a hidden logic woven into the fabric of reality itself? That's the journey we're about to take together. We'll explore the cutting-edge theories scientists used to explain this fine-tuning, from the multiverse hypothesis to the idea of a deeper, underlying order we haven't yet uncovered. We'll even step into the realm of philosophy, where thinkers have wrestled with this question for centuries, because this isn't just about stars and equations. It's about understanding our place in a universe that seems designed for discovery. By the end of this, you'll see the night sky differently. Every flicker of light, every silent orbit will feel like part of a grand, intentional masterpiece, and you're here to witness it. So let's begin. This mind-bending precision we see in the cosmos isn't just a casual observation. It's a full-blown scientific puzzle known as the fine-tuning problem. Picture the universe as an unimaginably complex machine where every dial, every setting, has to be adjusted to an exact value for life to even have a chance. Take gravity, for example. If it were just a tiny bit stronger, stars would burn out too quickly, leaving no time for planets to form or life to evolve. But if it were slightly weaker, matter wouldn't clump together at all, leaving the cosmos a cold, empty void. The same goes for the nuclear forces holding atoms together. Adjust them by a hair, and suddenly, the elements essential for life, like carbon or oxygen, wouldn't exist. This razor-thin margin for error is what scientists call the Goldilocks principle. Like the porridge in the fairy tale, the universe isn't too hot or too cold, it's just right. But here's where things get even more fascinating. This precision isn't limited to one or two constants. Over 20 different fundamental numbers, from the density of dark energy to the mass of electrons, all sit in this impossibly narrow sweet spot. The odds of this happening by chance astronomically low. Some calculations put it at 1 in 10 to the power of several hundred, a number so vast it's hard to even comprehend. So what does this mean? For some, it raises the tantalizing possibility of a multiverse, a cosmic landscape where countless universes exist, each with different physical laws. In most of them, conditions would be chaotic or barren, but in a rare few, like ours, everything clicks into place. It's like rolling a dice trillions of times until you finally land on the perfect sequence. Others argue that fine-tuning hints at something deeper, an underlying order or even an intentional design woven into the fabric of reality. Philosophers and theologians have wrestled with this idea for centuries, but now science is bringing hard data to the table. Whatever the explanation, one thing's certain: the fine-tuning problem forces us to rethink our place in the cosmos. Are we the unlikely winners of a cosmic lottery, or is there a profound reason why the universe seems tailor-made for life? The answer might just rewrite our understanding of existence itself. But here's where things get even more mind-bending. What if the universe seems perfect because we're the ones observing it? This is the heart of the anthropic principle, one of the most fascinating and debated ideas in cosmology. At its core, it suggests that the very fact we're here to ask these questions shapes how we perceive the universe's fine-tuning. Think of it like this: a fish might never question why water exists because, well, it's the only environment it's ever known. In the same way, could our existence blind us to the possibility that other universes, once utterly hostile to life, might be out there, unobserved because no one's around to witness them? This principle splits into two compelling interpretations. First, there's the weak anthropic principle, which boils down to observational bias. It's not that the universe was designed for us, but rather that we're observing it from the sliver of reality where conditions just happen to allow life. Imagine winning the lottery and then wondering, what are the odds? Well, someone had to win, and you're the lucky observer holding the ticket. Similarly, we might live in the one cosmic neighborhood where the numbers lined up, while countless other universes flicker in and out of existence, barren and unobserved. Then there's the strong anthropic principle, which takes things a step further. It proposes that our existence isn't just a fluke but somehow necessary, as if the universe had to produce conscious observers like us to give it meaning. Some versions of this idea even flirt with the notion that consciousness itself might play a role in shaping reality, a concept that bridges science and philosophy in startling ways. But here's the catch: does this explain fine-tuning, or does it just kick the question down the road? If the universe requires observers, what or who set that rule in motion? Critics argue that the anthropic principle feels like a cosmic shrug, an elegant way to sidestep the deeper mystery of why these precise conditions exist at all. Yet supporters counter that it's a vital reality check, reminding us that our perspective is unavoidably limited. After all, we can't stand outside the universe to see how typical or rare our circumstances really are. And that's what makes this idea so provocative. It doesn't just challenge how we see the cosmos, it forces us to confront the role of consciousness itself. Are we accidental witnesses to a grand coincidence, or is our presence somehow written into the fabric of existence? The answer might redefine not just our place in the universe, but the universe's place in us. The multiverse theory isn't just science fiction, it's a serious scientific proposal that could rewrite our understanding of reality. Imagine a cosmic tapestry where our universe is just one thread among an infinite number, each woven with its own unique set of physical laws. Some might be lifeless voids, others chaotic realms where matter tears itself apart, and a rare few, like ours, where conditions align perfectly for stars, planets, and life. This idea doesn't come from wild speculation, but from two of the most robust pillars of modern physics: quantum mechanics and inflationary cosmology. Let's start with quantum mechanics, the rulebook for the subatomic world. At this tiny scale, particles don't behave in fixed, predictable ways. Instead, they exist in a haze of probabilities, a shimmering cloud of possibilities until observed. Some interpretations suggest that every possible outcome of a quantum event actually happens, splitting reality into branching timelines. Now, stretch this idea to the cosmic scale. If every quantum possibility spawns a new universe, then an unfathomable number of parallel realities could exist, each with its own version of physics. Then there's inflationary cosmology, which describes how our universe exploded in size during the Big Bang. Leading theories propose that this expansion wasn't a one-time event but part of an endless cycle, with new universes constantly budding off like bubbles in a boiling pot. Each bubble universe could have different fundamental constants, some with gravity too weak for galaxies to form, others where atoms never stabilize. In this vast cosmic foam, a handful of universes would, by sheer chance, land on the precise settings needed for life. But here's the catch. Does this solve the fine-tuning problem, or does it just move the goalposts? If a multiverse exists, what determines its rules? Why should there be a mechanism that spawns universes at all? Critics argue that invoking infinite worlds to explain our unlikely perfection is like using a mystery to solve a mystery. And there's another wrinkle. If other universes are forever beyond our observation, can we ever truly test this idea? Some scientists hunt for clues in the cosmic microwave background, ghostly echoes of the Big Bang, where collisions with other universes might leave faint scars. Others explore mathematical consistency, asking whether a multiverse is the only way to explain certain quirks in quantum theory. Yet even if the multiverse is real, it raises profound questions about our place in existence. Are we just statistical noise in an endless sea of failed universes? Or does our ability to ponder these ideas hint at something deeper? The multiverse doesn't just challenge our understanding of physics, it forces us to confront what it means to be here, in this universe, asking these questions at all. Whether it's the ultimate answer or just another step in the journey, one thing's clear: the cosmos is far stranger and far more generous than we ever imagined. What if our universe's perfection isn't just luck, but a clue that we're missing entire dimensions of reality? That's the bold claim at the heart of string theory, one of the most ambitious ideas in modern physics. Forget the three dimensions we know: length, width, and height, or even the fourth we call time. String theory proposes that tiny, vibrating strands of energy, smaller than atoms, dance through 11 dimensions, their harmonies shaping everything from gravity to the particles that build our world. And here's the kicker: these hidden dimensions might be the reason the universe's constants are so exquisitely balanced. Think of it like this. Imagine the cosmos as a grand piano. The notes we hear, the forces and particles we observe, are just the keys we can press, but the piano's true richness comes from its hidden strings, resonating in ways we can't see. In string theory, those extra dimensions could be curled up so tightly they're invisible to us, like a garden hose that looks like a line from far away. Yet their geometry might dictate why gravity is just strong enough to hold galaxies together but weak enough to let stars breathe, or why the nuclear forces allow atoms to exist at all. This isn't just wild speculation. String theory emerged from a genuine crisis in physics. For decades, scientists struggled to reconcile Einstein's relativity, which governs the vast cosmos, with quantum mechanics, which rules the subatomic world. The two theories clash violently at extremes like black holes or the Big Bang. But string theory offers a breathtaking solution. If all particles are just different vibrations of these tiny strings, then everything, gravity, light, matter, stems from the same fundamental source. It's a cosmic symphony where every law of physics finds its place in the score. The implications for fine-tuning are staggering. If those hidden dimensions have specific shapes, like a six-dimensional Calabi-Yau manifold, a favorite among theorists, their structure could mathematically require the constants we observe. Picture a lock with billions of possible combinations. Only a few would open the door to a stable universe, and string theory suggests our dimensions are the perfect key. Some versions even predict a landscape of possible universes, each with different dimensional geometries, placing our finely tuned cosmos in a vast but explainable context. Yet for all its elegance, string theory remains controversial. No experiment has yet detected these extra dimensions or the strings themselves. Critics argue it's more math than physics, a beautiful idea without proof. But supporters counter that its mathematical consistency is too compelling to ignore, like a puzzle where all pieces fit. And if future tech, like particle colliders or gravitational wave detectors, ever finds evidence, it would revolutionize our understanding of why the universe feels so perfectly tailored. Whether string theory holds the answer or not, it reshapes how we see reality. Those hidden dimensions challenge us to think bigger, to imagine that the cosmos might be far grander, stranger, and more interconnected than we ever dreamed. And if we're right, the universe's perfection isn't an accident. It's a signature written in dimensions we're only beginning to decode. The universe we can see, stars, planets, galaxies, is barely the tip of the cosmic iceberg. In reality, over 95% of everything that exists is completely invisible to us, hidden in the form of dark matter and dark energy. These aren't just minor players in the cosmic story. They're the unseen architects, silently shaping the universe's structure and expansion. Without them, galaxies would fly apart, stars would never have formed, and life as we know it would be impossible. But here's the real mystery: their presence isn't just a happy accident. The amounts of dark matter and dark energy appear precisely tuned to create a universe capable of hosting complexity. Let's start with dark matter, the universe's invisible scaffolding. Picture a spiderweb, delicate yet strong enough to catch prey. Dark matter works the same way. Its gravitational pull binds galaxies together, preventing them from spinning apart. Without it, the Milky Way would have torn itself to shreds long before our solar system even formed. But dark matter doesn't just hold things in place. It's the reason galaxies exist at all. In the early universe, tiny fluctuations in dark matter's distribution acted like gravitational seeds, pulling ordinary matter into the dense pockets that eventually became galaxies. If dark matter were even slightly more or less abundant, those seeds wouldn't have grown properly, leaving the cosmos a scattered, lifeless void. Then there's dark energy, the enigmatic force driving the universe to expand faster and faster. Unlike gravity, which pulls things together, dark energy pushes space itself apart, and its value is unimaginably precise. If dark energy were just a bit stronger, the universe would have expanded so rapidly that matter could never clump into galaxies. But if it were weaker, gravity would have won, causing the cosmos to collapse back in on itself long before life had a chance to emerge. The balance between these two forces, dark energy's push and dark matter's pull, is so delicate that even a tiny shift would render the universe sterile. So why does this matter? Because dark matter and dark energy aren't just curiosities. They might hold the key to understanding why the universe is so finely tuned. Some theories suggest these mysterious components are tied to deeper, undiscovered laws of physics, perhaps even extra dimensions or quantum fields we haven't yet detected. Others propose that their values aren't arbitrary but emerge from some fundamental principle, like the way pi emerges from the geometry of a circle. And then there's the multiverse angle. In a sea of universes with different amounts of dark matter and energy, ours might be one of the rare islands where the numbers lined up just right. Yet for all their importance, we still don't know what dark matter and dark energy actually are. Dark matter could be made of undiscovered particles, streaming through us right now without a trace. Dark energy might be the energy of empty space itself, or evidence of a flaw in Einstein's theory of gravity. Every experiment, from deep underground detectors to space telescopes mapping the cosmos, brings us closer to answers, but the mystery endures. What's clear is this: dark matter and dark energy aren't just footnotes in the story of the universe. They are central characters, silently ensuring the stability and structure that make life possible. Their precise, almost orchestrated values suggest that cosmic perfection isn't just about the laws we see, it's about the hidden forces we're only beginning to uncover. And that might be the most profound clue yet in our quest to understand why the universe feels so perfectly designed. The cosmic microwave background isn't just a faint glow in the sky, it's a time capsule, a whisper from the universe's very first moments. Imagine peeling back the layers of space and time until you're staring at the aftermath of the Big Bang itself, frozen in light. That's what scientists see when they study the CMB, a nearly uniform sea of microwave radiation stretching across the entire cosmos, cooler than the deepest void yet brimming with secrets. But what makes this ancient light so extraordinary isn't just its age, it's the story it tells about how perfectly balanced our universe truly is. At first glance, the CMB appears almost too smooth, like a sheet of glass stretched across the sky. But peer closer and you'll spot tiny ripples, fluctuations in temperature no larger than 1 part in 100,000. These minuscule imperfections are cosmic gold. They're the gravitational seeds from which everything we know, galaxies, stars, planets, eventually grew. Without them, matter would have spread too evenly, leaving the universe a featureless desert. Yet here's the puzzle: those fluctuations are exquisitely calibrated, too strong, and the universe would have collapsed into black holes before stars could form. Too weak, and matter would never have clumped together at all. The CMB's delicate balance isn't just lucky, it's necessary for our existence. This precision is where cosmic inflation theory enters the picture. Think of the early universe as a balloon inflating faster than light itself. In a fraction of a second, quantum fluctuations, those tiny, random jitters at the smallest scales, were stretched to cosmic proportions, imprinting their pattern onto the CMB. Inflation doesn't just explain why the universe is so uniform. It suggests that fine-tuning might be baked into the fabric of reality. The CMB's fluctuations match predictions with eerie accuracy, as if the universe had a blueprint from the very beginning. But the CMB's clues don't stop there. Its polarization patterns, subtle swirls in the light's orientation, hint at gravitational waves from the Big Bang, ripples in space-time that could reveal even deeper laws of physics. Some researchers believe these patterns might point to extra dimensions or a multiverse, where our universe is one bubble among countless others. Others see them as evidence of a fundamental symmetry, a mathematical elegance underlying all of existence. What's truly humbling is how much we've learned from this faint afterglow. The CMB isn't just a relic, it's a mirror reflecting back the universe's flawless architecture. Every measurement, every new detail reinforces the same astonishing truth. The cosmos isn't just orderly, it's meticulously crafted. Whether through inflation, multiverses, or some deeper principle we've yet to uncover, the CMB stands as a testament to the universe's perfection. And as technology advances, this ancient light may yet reveal even grander truths about where we came from, and why the cosmos seems to welcome us so warmly. Earth isn't just another planet, it's a cosmic oasis perfectly positioned in what astronomers call the Goldilocks zone. This narrow band around a star isn't too close, where oceans would boil away, nor too far, where everything freezes solid. It's the sweet spot where water stays liquid and life as we know it can flourish. But here's the staggering part: Earth's ideal location isn't just about distance from the sun. It's about a combination of factors so finely tuned that even slight shifts could render our planet barren. Take our solar system as an example. Venus, Earth's neighbor, sits just a bit closer to the sun, but that small difference creates a hellish world with surface temperatures hot enough to melt lead. Mars, on the other hand, is slightly farther out, and while it once had flowing water, its thin atmosphere and frigid conditions make it a frozen desert today. Earth, nestled perfectly between them, enjoys just the right amount of solar warmth to keep water liquid and cycles stable. But what makes this even more remarkable is that our Sun itself is a Goldilocks star, not too big, not too small, burning steadily for billions of years without the violent flares that would sterilize nearby planets. Yet Earth's perfection doesn't stop there. Our planet's size and composition play starring roles too. A smaller world wouldn't have enough gravity to hold onto a life-sustaining atmosphere, while a larger one might trap too much heat or crush complex chemistry under its weight. Even Earth's molten core, generating a protective magnetic field, is a rare feature shielding life from deadly cosmic radiation. And let's not forget the Moon, whose gentle tug stabilizes Earth's tilt, preventing wild climate swings that could turn continents into wastelands. Now, with telescopes like Kepler and James Webb, we've discovered thousands of exoplanets, some orbiting their stars' habitable zones. Worlds like Kepler 442b or TRAPPIST-1e spark excitement, but here's the catch. Just being in the Goldilocks zone doesn't guarantee life. A planet might have the right temperature but lack water, or it could be tidally locked with one side scorched and the other frozen. Others might orbit unstable stars bombarded by radiation. The more exoplanets we find, the clearer it becomes. Earth's habitability isn't just about location. It's a symphony of conditions, each note precisely tuned. This raises a profound question. Is Earth's perfection a fluke, or is the universe teeming with life waiting to be found? Some scientists argue that given enough time and enough planets, life becomes inevitable, a natural outcome of cosmic chemistry. Others counter that the odds of all these factors aligning twice are vanishingly small. But perhaps the answer lies somewhere in between. Maybe the universe is capable of creating life, but only under the rarest, most exquisite circumstances. Every new exoplanet discovery chips away at the mystery, revealing how delicate the balance truly is. The Goldilocks zone isn't just a region of space, it's a mirror, reflecting back how astonishingly fragile and precious our existence really is. And as we peer deeper into the cosmos, we're not just searching for other Earths, we're unraveling the deepest question of all. In a universe of unimaginable vastness, are we alone, or is life woven into the very fabric of reality? There's something almost magical about the way mathematics describes our universe. Take Einstein's equation E equals mc squared. A handful of symbols that unravel the relationship between energy and matter, shaping everything from nuclear power to the life cycles of stars. Or consider the delicate dance of quantum mechanics, where probabilities and wave functions predict the behavior of particles with uncanny precision. It's as if the cosmos runs on an invisible code, and mathematics is the cipher that unlocks it. But this raises a profound question. Is math merely a tool we've invented to make sense of the world, or is it something deeper, a fundamental feature of reality itself? The idea that math might be woven into the fabric of the universe isn't new. Pythagoras, the ancient Greek philosopher, believed numbers were the essence of all things, and Galileo famously declared that nature is a book written in the language of mathematics. Fast forward to today, and this perspective finds startling support in modern physics. Think about the way fractals repeat in coastlines and galaxies, or how the Fibonacci sequence appears in sunflower spirals and hurricanes. Even the forces that govern atoms adhere to mathematical symmetry so precise they feel almost artistic. When physicists describe these patterns, they're not forcing equations onto nature. They're uncovering a pre-existing order, one that seems to have been there long before humans ever counted to 10. Yet not everyone agrees. Some argue math is a human invention, a mental framework we project onto chaos to find meaning. After all, the number 2 doesn't exist in the wild. It's an abstraction we created to describe pairs of things. But here's the counterpoint. If math were purely imaginary, why does it predict phenomena like black holes or quantum entanglement before we even observe them? When Paul Dirac wrote down an equation describing the electron, it implied the existence of antimatter, a particle no one had seen. Years later, antimatter was detected exactly as his math had foretold. Coincidence or evidence that math is more than just scribbles on a page? This debate touches the heart of why the universe feels so perfectly tuned. If math is inherent to reality, then the cosmos isn't just orderly, it's logical, built on principles that transcend time and space. String theory's extra dimensions, the symmetries of particle physics, even the way galaxies cluster like nodes in a cosmic network, all point to a reality where mathematics isn't just descriptive but generative. It's as if the universe isn't merely following rules, it's made of them. So where does this leave us? Perhaps the deepest clue to the universe's perfection lies in the sheer elegance of its equations. Whether math is discovered or invented, its power to reveal the cosmos's secrets suggests a connection far richer than we've yet grasped. And if that's true, then every time we solve an equation or decode a physical law, we're not just doing science, we're reading the universe's hidden blueprint, one breathtaking line at a time. Symmetry isn't just a pleasing aesthetic, it's the hidden scaffolding of reality itself. Look around and you'll find it everywhere. The spiral arms of galaxies mirroring the curves of seashells, the hexagonal perfection of snowflakes, even the bilateral symmetry of our own bodies. These patterns aren't accidents. They're signatures of deeper laws that govern everything from the smallest particles to the vast cosmic web. But what's truly astonishing is how symmetry doesn't just describe the universe, it shapes it, dictating the rules that make matter, energy, and even life possible. Take snowflakes, for example. Each one forms when water molecules arrange themselves into a crystalline lattice, a process guided by the fundamental symmetries of atomic bonds. No two snowflakes are identical, yet all obey the same six-fold symmetry, a reflection of nature's unshakable rules. Zoom out to the cosmos, and you'll see the same principle at work. Galaxies spin with a graceful balance, their shapes governed by gravity's invisible hand. Even the Big Bang itself was a moment of near-perfect symmetry, a primordial fireball where energy and matter were evenly distributed. Yet here's the twist: if that symmetry had never broken, if the universe had remained perfectly uniform, stars, planets, and life would never have formed. The flaws, the tiny imperfections, are what made us possible. This paradox lies at the heart of particle physics. In the subatomic realm, symmetries aren't just visual, they're mathematical, dictating how particles interact and transform. The Standard Model, our best map of the quantum world, is built on symmetries so precise they feel like poetry. But just as with the early universe, it's the breaking of these symmetries that creates richness. Consider the Higgs field, an invisible energy blanket that fills all space. In the first moments after the Big Bang, it was perfectly symmetrical, treating all particles equally. Then, as the cosmos cooled, that symmetry shattered, endowing some particles with mass while leaving others, like photons, weightless. Without this cosmic imperfection, atoms couldn't exist, and neither could we. The pursuit of symmetry has led physicists to some of their most profound breakthroughs. When Einstein unified space and time into a single fabric, he revealed a symmetry hidden in plain sight, a clue that the universe operates on principles far deeper than our everyday intuition. Later, physicists like Fermi showed that every symmetry corresponds to a conservation law, linking the elegance of math to the tangible world. Energy is conserved because the laws of physics don't change over time. Momentum is conserved because those laws are the same in every direction. Symmetry, in other words, isn't just beautiful, it's functional, a cosmic cheat code that lets us decode reality. Yet for all its power, symmetry alone can't explain the universe's fine-tuning. If everything were perfectly balanced, we'd live in a static, lifeless void. It's the subtle asymmetries, the cracks in the cosmic mirror, that allow complexity to emerge, the fact that matter slightly outnumbered antimatter in the early universe. The way DNA's twisted ladder prefers a left-handed twist over a right-handed one, these quirks might seem like exceptions, but they're the exceptions that make the rule, the delicate imbalances that let stars burn and cells divide. So is symmetry proof of the universe's perfection? In a way, yes, but not in the way you might think. The cosmos isn't perfectly symmetrical. It's perfectly imperfect, balancing order and chaos in a dance that allows for galaxies, planets, and minds to ponder it all. And that might be the most profound symmetry of all, the harmony between structure and surprise, between the laws that bind and the flaws that set us free. Imagine waking up one day, no body, no world, just a lone brain drifting through an endless void, conjuring all of reality as a fleeting hallucination. Sounds like the plot of the strangest sci-fi movie ever, right? But this isn't fiction. It's the Boltzmann brain paradox, a thought experiment so unsettling it shakes the foundations of how we understand the universe's longevity and our place in it. The idea comes from 19th century physicist Ludwig Boltzmann, who suggested that in a universe that lasts forever, random fluctuations could, given enough time, spontaneously assemble anything, even a fully formed, conscious brain, complete with false memories of a life that never existed. Here's where it gets even wilder. If the cosmos truly is eternal, the odds of such a brain popping into existence might actually be higher than the odds of an entire, orderly universe like ours evolving naturally. Think of it like shaking a box of Scrabble tiles forever. Eventually, they'll spell out a Shakespeare sonnet purely by chance. So why aren't we all just these disembodied Boltzmann brains hallucinating reality into being? The paradox forces us to confront a chilling possibility. If randomness can create consciousness, how do we know we're not the statistical flukes? This isn't just philosophical musing, it's a direct challenge to cosmic fine-tuning. If the universe is perfectly calibrated for life, why would isolated brains floating in space be more probable than stable, life-friendly worlds? Some scientists argue this paradox exposes a flaw in theories that rely on infinite time or a multiverse. After all, in an endless cosmic ocean, shouldn't the most likely observers be these chaotic, momentary aberrations rather than beings embedded in a 13.8 billion-year-old universe with consistent laws? Yet there's a counter-argument. The fact that we do observe a coherent, ancient cosmos might be evidence that the universe isn't eternal in the way Boltzmann imagined. Perhaps it had a definitive beginning, like the Big Bang suggests, putting limits on how much randomness can accumulate. Or maybe the laws of physics inherently discourage such freak fluctuations, making structured reality far more probable than a lone brain hallucinating stars and galaxies. The Boltzmann brain paradox doesn't just bend our minds, it forces us to ask what counts as real in the grand scheme of things. Are we the product of meticulous cosmic fine-tuning, or just a fleeting glitch in an infinite void? The answer might lie in the very fabric of reality, whispering that the universe isn't just old or vast, but intentional, a place where true observers arise from stardust, not statistical noise. And that makes all the difference. At the smallest scales, the universe defies our everyday intuition in the most astonishing way. What looks like empty space to our eyes is actually a seething, bubbling quantum foam where particles wink in and out of existence in the blink of an eye. These quantum fluctuations aren't just theoretical curiosities. They might hold the key to understanding how our finely tuned cosmos came to be. Imagine a calm ocean surface suddenly erupting with tiny, fleeting waves, each one appearing and vanishing before you can even point to it. That's the quantum vacuum, never truly still, always alive with potential. These microscopic energy bursts might seem insignificant, but their implications are cosmic. In the very first moments after the Big Bang, quantum fluctuations could have been the seeds of everything we see today. Picture stretching a tiny wrinkle in space-time to the size of the observable universe. Those initial irregularities, magnified by inflation, became the gravitational scaffolding for galaxies and galaxy clusters. Without those quantum ripples, matter might have spread too evenly, leaving the cosmos a featureless void. Instead, we have a structured, dynamic universe where stars ignite and planets form. But the quantum realm's strangeness goes deeper. Heisenberg's uncertainty principle tells us that empty space can't ever be truly empty. At any moment, pairs of virtual particles, matter and antimatter, pop into existence, borrowing energy from the vacuum before annihilating each other in a flash. Normally, this dance happens too quickly to notice, but under extreme conditions, like near a black hole's event horizon, these particles can become real, stealing energy from the black hole itself in a process called Hawking radiation. It's as if the universe has built-in creativity, constantly generating and recycling energy at the smallest scales. What's truly mind-bending is how this quantum chaos leads to cosmic precision. The same fluctuations that allow particles to appear from nothing also set strict limits on how much energy can emerge, governed by Planck's constant, a number so finely tuned that even a slight change would unravel atomic stability. The quantum world is a paradox, unpredictable in individual events, yet astonishingly reliable in the aggregate, like a casino where every single spin of the roulette wheel is random, but over time the house always wins. This delicate balance between randomness and order might be the universe's greatest trick. Quantum fluctuations inject just enough chaos to allow for novelty, like the formation of galaxies, while the underlying laws ensure stability, keeping atoms from disintegrating and stars from burning out unpredictably. Some theorists even suggest that the vacuum energy driving the universe's expansion could be the cumulative effect of these endless quantum flickers, a vast sea of microscopic tremors shaping the cosmos on the grandest scale. So when we marvel at the universe's perfect tuning, we're not just talking about gravity or the speed of light. We're acknowledging the quantum undercurrents that set the stage for it all. The same uncertainty that allows particles to defy expectations might also be the reason our universe is anything but random, a place where chance and necessity dance together, creating a cosmos precise enough for life and mysterious enough to keep us forever in awe. The cosmos stretches across billions of light years, filled with countless stars and planets, so why does it feel so empty? This is the heart of the Fermi paradox, a question that haunts astronomers and philosophers alike. If the universe is so finely tuned for life, why haven't we found any trace of other civilizations? The numbers seem to be in our favor. With hundreds of billions of galaxies, each containing billions of stars, and countless planets orbiting in habitable zones, the odds suggest we should have heard something by now. A single cosmic whisper, a flicker of artificial light, even the faintest radio signal, yet all we hear is silence. One explanation is the rare Earth hypothesis, the idea that while the universe may be vast, the conditions that make a planet truly hospitable are staggeringly specific. Earth isn't just lucky, it's miraculous. Consider our position in the Milky Way, far enough from the galactic center to avoid deadly radiation, but close enough to have a rich supply of heavy elements needed for life. Our sun is stable, our moon stabilizes our climate, and our planet's geology recycles carbon to regulate temperatures over eons. Even the way Jupiter acts as a cosmic shield, deflecting asteroids that might otherwise bombard us, feels like a carefully arranged cosmic safety net. Could it be that while life-friendly planets exist, the combination of factors needed for intelligent life to arise and thrive is vanishingly rare? But here's the twist: what if the silence isn't about rarity, but timing? The universe is 13.8 billion years old, but Earth didn't form until 2/3 of that history had already passed. Civilizations might have risen and fallen long before we existed, their signals lost in the vastness of time. Or perhaps advanced societies don't last long enough to make contact, self-destructing through war or ecological collapse before they can reach the stars. The Fermi paradox forces us to confront an uncomfortable possibility. Maybe the universe is perfect for life, but the window for civilizations to find one another is impossibly narrow. Then there's the darker alternative that we're not just alone, but first. If life requires such precise conditions, Earth might be one of the earliest planets where it could even emerge. In this scenario, the cosmos is still waking up, and humanity could be the pioneers, the ones who define what intelligence in the universe looks like. It's a humbling thought, but also an exhilarating one. The silence isn't a sign of absence, it's an invitation. Whether the answer lies in rarity, timing, or something stranger, the Fermi paradox and rare Earth hypothesis remind us that cosmic perfection doesn't guarantee companionship. The universe may be fine-tuned for life, but life itself, especially the kind that builds cities and sends signals to the stars, might be the rarest jewel of all. And that makes our existence not just a happy accident, but a story still being written, one quiet night sky at a time. Life emerges from an intricate ballet of molecules, each step so precise it borders on the miraculous. Take DNA, the blueprint of all living things. Its double helix structure doesn't just store information, it replicates with near-perfect accuracy, thanks to enzymes that proofread and correct errors as they go. But here's the astonishing part. These molecular machines operate at speeds and efficiencies that defy randomness. If DNA replication were even slightly less accurate, mutations would overwhelm life before it could evolve. If enzymes were a fraction slower, cells couldn't keep up with the demands of growth or repair. The margins for error are vanishingly thin, yet here we are, products of a system that gets it right billions of times a day. This biochemical precision isn't isolated, it's deeply entwined with the universe's physical constants. Consider the carbon atom, the backbone of life as we know it. Carbon's ability to form 4 stable bonds, creating chains and rings of staggering complexity, hinges on the exact strength of the nuclear force. If this force were just a few % stronger or weaker, carbon wouldn't exist in the quantities needed for life. Even water, the universal solvent, owes its life-giving properties to a delicate balance of hydrogen bonds forces shaped by the same quantum rules that govern stars. It's as if the cosmos conspired to create the perfect conditions not just for planets, but for the chemistry that animates them. The fine-tuning goes deeper. Enzymes, the molecular workhorses of biology, rely on atomic geometries so precise they're like locks and keys. The enzyme that helps your muscles contract, for instance, fits its target molecule with an accuracy akin to landing a spaceship on a dime. This specificity depends on the electromagnetic force being exactly as strong as it is any variation, and these interactions would fail. Even the way cells harvest energy through the dance of electrons in mitochondria reflects a cosmic harmony. The energy levels of electrons set by quantum mechanics align perfectly with the needs of living systems. Some scientists argue this isn't coincidence but evidence of a deeper principle. That life isn't just an accident in a hospitable universe, but an inevitable outcome of its laws. The universe seems biased toward complexity, with constants that favor the emergence of molecules complex enough to store information, adapt, and evolve. From this perspective, biology isn't separate from cosmology. It's the universe's way of understanding itself. Yet the mystery remains. Why does reality lean so decisively toward life? Is this the only possible universe where life could arise, or are we seeing one thread in a vast tapestry of possibilities? The answer might lie in the coming together of two great narratives, the story of the cosmos and the story of life, revealing a truth more profound than either alone. Every cell in your body, every strand of DNA, hums with the resonance of a universe that didn't just allow life but invited it, and that changes everything. What if everything we perceive as reality, the stars, the laws of physics, even our own thoughts, is nothing more than lines of code in an unfathomably advanced simulation? This is the core of the simulation hypothesis, a theory that takes cosmic fine-tuning and flips it on its head. Instead of asking why the universe seems perfectly designed for life, it proposes a startling answer, because it was designed not by a deity, but by beings with technology so advanced their simulations are indistinguishable from reality. Think of it like a video game so immersive, the characters inside believe their world is real. Now scale that up to an entire universe with every quark, every galaxy meticulously rendered. The idea isn't as far-fetched as it sounds. Philosopher Nick Bostrom formalized the argument in 2003, breaking it down into a chilling trilemma. Either civilizations like ours always go extinct before developing simulation technology, or they choose not to run ancestor simulations, or here's the kicker, we're almost certainly living in one. Why? Because if even one civilization reaches the capability to simulate conscious beings, they could create countless virtual worlds, each populated with minds as complex as ours. Statistically, the odds would overwhelmingly favor us being among the simulated rather than the original. But where's the evidence? Some scientists point to glitches in the fabric of reality, tiny, unexplained anomalies that could be artifacts of imperfect code. Ever experienced déjà vu, that eerie feeling you've lived a moment before? Or noticed how particles at the quantum level behave differently when observed, as if the simulation conserves processing power by only rendering details when needed? Even the universe's pixelated nature, the fact that space, time, and energy come in discrete, indivisible units like Planck lengths, could hint at a computational framework. Yet for all its intrigue, the simulation hypothesis faces fierce criticism. Physicists like Sabine Hossenfelder argue that it's untestable by definition. If a simulation is perfect, how could we ever detect its seams? Others counter that simulating an entire universe would require energy and resources beyond any conceivable technology, even for a hyper-advanced civilization. And then there's the philosophical objection. If we're simulations, are our choices and emotions just illusions? Does meaning itself collapse into lines of binary? Perhaps the most profound implication isn't whether the theory is true, but what it reveals about our hunger for explanation. The simulation hypothesis, like religion or multiverse theory, offers a narrative to ease the vertigo of cosmic fine-tuning. It's a mirror reflecting our deepest question: why does reality feel so intentional? Whether the answer lies in code, cosmology, or something stranger, one thing's certain: the universe's perfection keeps us searching, questioning, and marveling at the possibility that there's far more to existence than meets the eye. The universe has a strange obsession with disorder. From the moment of the Big Bang, everything has been sliding toward chaos according to the ruthless law of entropy, the measure of a system's disorder. Hot stars cool, complex molecules break down, even mountains crumble to dust. Yet here we are, alive in a universe that seems hell-bent on decay, building intricate structures like cells, brains, and civilizations against the cosmic tide. How does life not just survive but thrive in this relentless march toward disorder? The answer lies in one of physics' most profound paradoxes. Entropy doesn't just destroy, it creates the very conditions for complexity to emerge. Picture a campfire. As the wood burns, its orderly structure collapses into smoke and ash, a textbook example of increasing entropy. But look closer. The heat from that fire warms your skin, drives chemical reactions in your body, even fuels the thoughts in your brain as you ponder the flames. The energy dispersing into the night isn't just chaos, it's potential. This is entropy's hidden gift. By spreading energy unevenly, it creates pockets where work can be done. Stars shine because heat flows from their cores to cold space. Plants grow because sunlight scatters into the Earth's cooler surface. Life itself is a symphony of controlled entropy, channeling chaos into temporary islands of order. The arrow of time, the one-way street from past to future, is stitched into this dance. When you watch an egg crack, you never see the yolk leap back into its shell. That irreversible flow is entropy in action, and it's why we remember the past but not the future. Yet this same arrow shapes the universe's perfection. In the beginning, the cosmos was a hot, smooth soup of particles. As entropy increased, imperfections emerged, tiny density variations that gravity amplified into galaxies. Without entropy's push toward disorder, the universe would have remained featureless, sterile. The very chaos we fear made structure possible. Life takes this further. Organisms are masterful at playing the entropy game. A single cell maintains its intricate machinery by constantly exporting disorder, flushing waste, shedding heat, recycling damaged parts. Forests and coral reefs thrive by creating localized complexity while exporting entropy to their surroundings. Even human civilization follows the pattern. Cities organize energy into buildings and networks, while radiating waste heat into the atmosphere. The universe allows these oases of order not despite entropy, but because of it. The second law of thermodynamics isn't a death sentence, it's an instruction manual for building complexity in a world where energy flows downhill. This reveals a breathtaking truth about cosmic fine-tuning. The universe's constants don't just permit life, they ensure entropy unfolds in a way that makes life inevitable. If gravity were weaker, matter wouldn't clump enough to form stars. If the nuclear force were stronger, atoms wouldn't release energy gradually. Even the expansion rate of space is tuned so entropy increases fast enough to drive evolution but slow enough for structures to persist. Time's arrow isn't just pointing toward chaos, it's carving a path where complexity can bloom. So next time you see autumn leaves wither or a sandcastle wash away, remember, decay isn't the whole story. Entropy is the universe's way of making room for something new, a cosmic rhythm where every ending feeds a beginning. The perfect balance between order and disorder isn't an accident, it's the silent architect of everything we know. Black holes are often painted as cosmic monsters, devouring everything that strays too close. But what if these gravitational behemoths aren't just destroyers? What if they're also creators, the architects of new universes hidden within their depths? This mind-bending idea isn't science fiction. It's the heart of conformal cyclic cosmology, a theory proposed by physicist Roger Penrose. Imagine our universe's distant future, trillions of years from now, when all stars have burned out and even black holes evaporate into faint whispers of radiation. In this cold, empty expanse, Penrose suggests something extraordinary happens. The universe resets, space becomes smooth and featureless, stretching until it resembles the hot, dense state of the Big Bang itself. The end of one cosmos becomes the birth of another, in an endless cycle of death and rebirth. But how do black holes fit into this grand cycle? Their role might be more profound than we ever imagined. As a black hole evaporates via Hawking radiation, it doesn't just fade away, it leaves behind a hidden imprint, a sort of cosmic fingerprint encoded in the fabric of space-time. Penrose calls these imprints Hawking points, and he believes they could be echoes of previous universes, scars left behind in the newborn cosmos. Even wilder, some theories suggest that the singularity at a black hole's core, a point of infinite density, might not be an end at all, but a bridge. Could the crushing gravity inside a black hole spawn an entirely new universe with its own laws of physics, branching off from our own like a cosmic seed? This idea isn't just poetic. It could explain one of the universe's deepest mysteries, its improbable fine-tuning. If black holes are birthing new universes, each with slightly tweaked physical constants, then over countless cycles, only the universes with just right conditions, like ours, would survive long enough to harbor life. The others would collapse or stagnate, lost to cosmic selection. In this way, black holes might not just recycle matter, they could refine existence itself, sculpting each new universe closer to perfection. Yet the implications go even further. If black holes are cosmic recyclers, they challenge our very understanding of time and causality. In a multiverse of branching black hole universes, cause and effect might not flow in a straight line. An event in our future could influence the birth of a universe in our past, weaving a tapestry of existence where beginnings and endings blur. It's a vision of reality where destruction and creation are two sides of the same coin, where the darkest objects in the cosmos might also be the brightest beacons of renewal. Of course, not all scientists are convinced. Critics argue that these ideas stretch physics beyond what we can test, venturing into the realm of metaphysics. But Penrose and others point to faint patterns in the cosmic microwave background, the afterglow of the Big Bang, as potential evidence of these cyclic universes. Whether the theory holds up or not, one thing's certain: black holes continue to defy our expectations, reminding us that the universe's perfection might not be a one-time miracle, but the result of an endless, elegant dance of endings and beginnings. The holographic principle turns everything we know about reality inside out, literally. Imagine standing in front of a mirror, but instead of reflecting your surface, that mirror contains every detail of your body, your thoughts, even the air around you, encoded flawlessly on its glass. Now scale that up to the universe. What if the three-dimensional cosmos we experience, the swirling galaxies, the curve of space-time, even our own consciousness, is just a projection, a hologram etched onto a distant two-dimensional surface? This isn't science fiction. It's a serious theory born from the clash between quantum mechanics and black hole physics, and it might just hold the key to why the universe feels so perfectly tuned. The idea first took shape when physicists grappling with black holes stumbled on a paradox. According to quantum mechanics, information, the building blocks of reality, can never be destroyed. Yet when matter falls into a black hole, it seemingly vanishes without a trace. The solution: maybe the information isn't lost. Maybe it's smeared across the black hole's event horizon, the point of no return, like a cosmic hard drive storing data in a thin, two-dimensional shell. Take this further and you arrive at a staggering possibility. If a black hole's interior can be described entirely by information on its surface, could the same be true for the entire universe? This is the holographic principle in action. It suggests that everything we perceive as three-dimensional, the depth of space, the texture of matter, is actually encoded on a boundary we can't see, like a movie playing on the walls of reality's theater. Think of a credit card hologram. Tilt it, and a 3D image appears, even though all the data is stored flat. The universe might work the same way, with gravity and quantum fields emerging from a deeper, flatter layer of information. If true, it would mean the cosmos isn't just governed by laws, it is those laws, written in a geometric code we're only beginning to decipher. But how does this explain fine-tuning? Here's where things get even stranger. In a holographic universe, the apparent precision of physical constants, the strength of gravity, the speed of light might not be fundamental at all. They could be derived properties like shadows cast by a deeper, more elegant structure. Picture a chess game where the rules seem arbitrary until you realize they're projections of a simpler, more universal game being played on a higher dimensional board. The holographic principle hints that what we call fine-tuning might just be the inevitable outcome of information processing at the universe's most basic level. Critics argue that the theory is still speculative, lacking direct experimental proof, yet supporters point to tantalizing clues, like the way calculations in string theory and quantum gravity often work more cleanly in lower dimensions. Some even suggest that the cosmic microwave background, the afterglow of the Big Bang, could hold subtle imprints of this holographic code. If they're right, the implications are earth-shaking. Reality, as we know it, would be a kind of illusion, a rich, interactive projection from a realm where space and time don't even exist. Whether the holographic principle holds up or not, it forces us to rethink perfection. If the universe is a hologram, its fine-tuning isn't a puzzle to solve. It's a signature, a hint that we're glimpsing reality through a veil, one layer short of the truth. And that's the most thrilling possibility of all, that the cosmos isn't just finely tuned, but fundamentally simpler than we ever dreamed, waiting for us to crack its two-dimensional cipher. What if the universe doesn't just exist around us, but because of us? This radical idea sits at the heart of one of the most provocative theories in physics, that consciousness isn't just a product of the cosmos, but a fundamental force shaping it. At first glance, it sounds like philosophy, but the roots of this idea dig deep into quantum mechanics. Take the double-slit experiment, where particles like electrons behave as waves when unobserved, spreading out in probabilities, but collapse into definite positions the moment we measure them. It's as if reality hesitates until a conscious observer steps in, forcing the universe to make up its mind. This isn't just lab curiosity, it hints at something profound. If observation affects quantum systems, could consciousness be woven into the fabric of reality itself? Some interpretations, like the von Neumann-Wigner hypothesis, take this further, suggesting that the collapse of quantum probabilities requires a conscious observer. Without minds to perceive it, the universe might remain a blur of possibilities, like a dream waiting to be dreamed. Even more startling, certain variations of quantum theory propose that consciousness isn't confined to brains, but is a universal property, like gravity or electromagnetism, with the cosmos itself possessing a rudimentary form of awareness. Eastern philosophies have danced around this idea for millennia. Hindu texts describe Brahman, the ultimate reality, as a cosmic consciousness manifesting the physical world through perception. Buddhist teachings frame reality as interdependent, where observer and observed arise together, neither existing in isolation. These ancient insights eerily echo modern quantum puzzles, as if two entirely different paths, science and spirituality, converged on the same truth, that the universe and the mind might be inseparable. But here's where the debate ignites. Critics argue that equating quantum observation with human consciousness is a leap. After all, in labs, a measurement can be as simple as a photon hitting a detector, no human needed. Yet proponents counter that detectors, too, are part of a chain leading back to conscious interpretation. Without someone to read the data, does the measurement even mean anything? This tension forces us to confront a deeper question. Is consciousness a rare spark in a mechanical universe, or is the universe itself a kind of living thought? The implications for cosmic fine-tuning are staggering. If consciousness plays an active role in shaping reality, the universe's perfection isn't just a happy accident, it's a collaboration. The constants of nature, the balance of forces, even the emergence of life might reflect a deeper reciprocity between mind and matter. Some theorists even speculate that advanced civilizations could one day harness this link, tweaking physical laws through collective observation like cosmic architects. Whether consciousness is a creator or a bystander, one thing's clear: the boundary between the observer and the observed is far blurrier than we ever imagined. And that might be the most tantalizing clue yet in our quest to understand why the universe feels so intimately, inexplicably right. Our brains are remarkable machines, fine-tuned by millions of years of evolution to track predators, build tools, and navigate social hierarchies, not to decipher the fundamental fabric of reality. Think about it, we perceive only a sliver of the electromagnetic spectrum, experience time in a linear trickle, and struggle to visualize dimensions beyond 3. So when we stare into the night sky, wrestling with questions of cosmic fine-tuning, we're like ants trying to comprehend the internet. The universe's perfection might not just be mysterious, it could be inherently incomprehensible to minds like ours. Consider how we process reality. Our intuition is wired for medium-sized objects moving at medium speeds, the world of apples falling and lions chasing. But at quantum scales, particles defy location and causality, while at cosmic distances, space itself stretches and warps, even our language falters. Try describing the curvature of spacetime without borrowing from everyday analogies like trampolines or rubber sheets. These aren't just knowledge gaps, they're cognitive barriers, hardwired limits to what our neural architecture can grasp. Yet history offers a glimmer of hope. Every scientific revolution began as an impossibility. Newton's gravity unified celestial and earthly motion. Einstein's relativity shattered absolute time, and quantum mechanics revealed a world where observation alters reality. Each time, humanity's collective intuition expanded to accommodate the unimaginable. Could the same happen with cosmic fine-tuning? Some theorists suggest we're on the brink of another paradigm shift, one where concepts like cause and purpose might be replaced by deeper, stranger frameworks. Imagine a physics where the universe's perfection isn't a puzzle to solve, but a natural consequence of laws we've yet to formalize. But there's a humbling alternative, that some truths simply transcend human cognition. Even in mathematics, certain proofs are so complex they're effectively unknowable to any single mind. The cosmos might operate on a similar scale, its elegance visible only in fragments, like shadows on a cave wall. This isn't defeatism, it's liberation. Embracing the unknown keeps science alive, a reminder that wonder, not mastery, might be our most authentic response to the universe's grandeur. Perhaps the answer lies in collaboration between human curiosity and artificial intelligence, between generations of thinkers, even between disciplines like physics and philosophy. The universe didn't promise us understanding, only the chance to keep reaching. And in that reaching, we might touch something profound, not the certainty of answers, but the beauty of the questions themselves. For thousands of years, humans have looked up at the stars and seen not just celestial bodies, but messages, signs of something greater at work. Across cultures and civilizations, the astonishing precision of the cosmos has inspired profound spiritual interpretations. Ancient Egyptians revered the sun god Ra as the architect of cosmic order, while Hindu scriptures describe Brahman as the divine essence sustaining universal harmony. The Abrahamic traditions speak of a creator who stretched out the heavens like a curtain, setting the stars in their courses with meticulous care. These aren't just poetic metaphors, they represent humanity's earliest attempts to explain the universe's breathtaking coherence. What's fascinating is how these theological perspectives often echo modern scientific discoveries in unexpected ways. Take the medieval Islamic scholars who saw God's hand in the mathematical perfection of planetary motion centuries before Kepler formulated his laws of orbital mechanics. Or consider how the Taoist concept of yin and yang, the dynamic balance of opposites, mirrors the delicate equilibrium between cosmic forces like gravity and dark energy. Even the Big Bang Theory finds a curious parallel in creation stories from the Maori to the Maya, where the universe emerges from a singular, explosive moment of genesis. Yet for all these resonances, science and spirituality have often been framed as opposing forces, one seeking natural explanations, the other invoking the supernatural. But what if this dichotomy misses the deeper truth? Many pioneering scientists were deeply spiritual. Newton saw his laws as revelations of divine craftsmanship, while Einstein famously marveled that the most incomprehensible thing about the universe is that it is comprehensible. For them, the mathematical elegance of physics wasn't a rejection of transcendence, but a pathway to it. This interplay between faith and empiricism takes on new urgency in our age of quantum physics and multiverse theories. Some theologians argue that a multiverse, with its countless universes governed by different physical laws, doesn't eliminate the need for a designer, but rather suggests a creator of unimaginable scope. Others propose that the fine-tuning we observe might reflect an even grander principle, that consciousness itself is fundamental, and the universe evolves toward self-awareness. These aren't retreats into mysticism, but serious engagements with science's frontier questions. Perhaps what unites these perspectives is a shared sense of wonder, the humility to acknowledge that whether through equations or prayer, we're all grappling with the same sublime mystery. When a Buddhist monk contemplates interdependence or a physicist traces the quantum entanglement of particles, both are recognizing a reality far more intricate than appearances suggest. The dialogue between these worldviews doesn't have to be a battle. It can be a collaboration, each offering unique tools to explore why existence is structured so exquisitely. In the end, whether one sees cosmic perfection as proof of divine artistry or emergent natural law, the quest for understanding remains our common ground. The universe invites our curiosity, rewarding both the telescope and the meditation cushion with glimpses of its grandeur. And that might be the most profound perfection of all, that in a cosmos vast enough to humble us, we still find ourselves drawn back, generation after generation, to ask the same awe-filled questions. The universe doesn't need a blueprint to build a galaxy, just gravity, a humble force acting on tiny particles of dust and gas. Over billions of years, those particles clump, collapse, and spin, weaving themselves into spirals of stars without a single architect calling the shots. This is the magic of emergence, the phenomenon where simple rules give rise to staggering complexity, like an invisible hand guiding chaos into order. Think of a murmuration of starlings where thousands of birds move as one fluid entity, each following nothing more than a few instinctive cues. No leader directs the flock, yet the result is a breathtaking dance, alive and ever-changing. The cosmos operates on the same principle. From the quantum froth to the cosmic web, complexity emerges not by design, but from the bottom up. Take water as another example. A single molecule has no concept of wetness, no ability to create ripples or waves. Yet when trillions of these molecules gather, they give rise to properties none possessed alone: fluidity, surface tension, the ability to carve canyons or cradle life. This is emergence in action, the whole becoming infinitely more than the sum of its parts. The same alchemy unfolds in every corner of reality. Atoms bond to form molecules, which build proteins, which assemble into cells, each step a leap into new complexity, guided by nothing more than the interplay of simple, relentless laws. Even consciousness itself may be an emergent phenomenon. Your brain is made of nearly 100 billion neurons, each a simple cell firing electrical pulses. None of them knows how to think, yet together they generate ideas, memories, and the very experience of being you. There's no ghost in the machine, just the staggering output of countless tiny interactions. This raises a tantalizing possibility. What if the universe's fine-tuning isn't the work of some cosmic watchmaker, but the inevitable result of self-organizing principles? Like a river carving its own path downhill, reality might naturally flow toward states of increasing complexity, with life and intelligence as its destination. Critics argue that emergence can't fully explain the universe's precision. After all, for simple rules to produce such intricate outcomes, those rules themselves must be exquisitely calibrated. But supporters counter that this misses the point. Emergence isn't random. It's a filter, a process that amplifies certain patterns while discarding others. In a multiverse of infinite possibilities, only the universes with rules capable of fostering complexity would ever be observed. The rest would remain barren, unremarkable, and unseen. What's truly humbling is how emergence bridges scales. The same principles that shape snowflakes also mold galaxies, suggesting a fractal harmony to existence. Whether you're staring at the branching veins of a leaf or the vast filaments of the cosmic web, you're witnessing the same story, simplicity birthing wonder again and again. And that might be the most profound perfection of all, not a static, preordained order, but a universe that creates its own majesty, one interaction at a time. Chance is the wild card in the universe's deck, an unpredictable force that reshapes destinies with a single roll of the cosmic dice. Picture Earth 4.5 billion years ago, a molten rock bombarded by asteroids. One of those collisions, a chance strike by a Mars-sized object, shattered our planet and birthed the Moon, a celestial accident that stabilized Earth's tilt and paved the way for stable climates and seasons. Without that random impact, life as we know it might never have gained a foothold. Yet for all its chaos, chance doesn't operate in a vacuum. It dances with determinism, the unyielding laws of physics that govern how particles collide, stars ignite, and galaxies spiral. The universe isn't just a game of luck. It's a symphony where randomness composes the melody and physical laws write the sheet music. Consider the humble carbon atom, the backbone of life. Its existence hinges on a bizarre quantum fluke called the Hoyle state, a precise energy level in the carbon nucleus that allows it to form in the hearts of stars. Without this exact resonance, stars would fuse helium into heavier elements, skipping carbon entirely. The odds of this state existing, astronomically slim. Yet here we are, because in a cosmos vast enough, even the rarest probabilities become inevitable. This isn't magic, it's the brute force of statistics playing out across billions of years and trillions of stars. The universe doesn't need to be fine-tuned. It just needs enough time and space for every possible outcome to manifest somewhere. But here's the twist: chance alone can't explain the universe's consistency. Gravity never forgets to pull. Light never decides to slow down on a whim. The laws themselves are the stage on which randomness performs. Imagine a river carving a canyon. The water's path is chaotic, tumbling over rocks in unpredictable ways, but the force of gravity guiding it downward never wavers. In the same way, quantum fluctuations might determine which galaxies form where, but the rules of relativity ensure those galaxies behave predictably once they exist. This interplay creates a universe that's both stable and dynamic, where the bedrock of reality is firm, but the details are gloriously messy. Life embodies this duality perfectly. Evolution is driven by random mutations, typos in DNA that could spell disaster or serendipity. Yet natural selection isn't random at all. It's a ruthless editor, preserving only the changes that enhance survival. The result, a planet teeming with creatures exquisitely adapted to their niches, not by design but by endless trial and error. The same principle applies to the cosmos. Asteroid strikes, supernova explosions, even the drift of stars within galaxies, these stochastic events shape the conditions for life, but they unfold within a framework of unbreakable physical laws. So is the universe's perfection just a numbers game? In one sense, yes. With infinite time and space, every possible configuration becomes inevitable, including the rare islands of order where life can thrive. But it's also more than that. The laws themselves seem curiously conducive to complexity, as if the deck were stacked in favor of structure rather than chaos. Whether by sheer probability or some deeper principle we've yet to uncover, the cosmos manages to balance randomness and order in a way that feels, against all odds, just right. And that's the real wonder, not that we exist, but that the universe makes our existence possible through a blend of chance and necessity, so exquisite it takes your breath away. Artificial intelligence is rapidly becoming the ultimate cosmic detective, sifting through the universe's data with a precision and speed no human mind could match. Picture this: a neural network trained on billions of galaxy images spots patterns invisible to our eyes, subtle distortions in starlight hinting at dark matter's hidden architecture. Or an AI simulating quantum vacuum fluctuations at scales so minute, it stumbles upon a previously unnoticed resonance that explains why matter outweighs antimatter. This isn't science fiction, it's happening now. Machine learning algorithms already analyze gravitational wave signals from colliding black holes, filter cosmic microwave background noise for echoes of the Big Bang, and even predict exoplanet compositions from atmospheric spectra. But what if these are just the first steps? The real revolution may lie in AI's ability to think outside the box of human intuition. Take quantum mechanics, a realm where particles exist in multiple states until observed, where causality loops back on itself, and where our classical notions of space and time break down. Human brains evolved to track lines, not quantum superpositions, but an AI, unshackled from our cognitive biases, might uncover connections we've missed for centuries. Imagine an algorithm designed to explore the mathematical landscape of string theory, testing billions of configurations to find those that produce stable universes like ours. It could identify commonalities we'd never spot, revealing whether our physical constants are lone outliers or inevitable outcomes of deeper symmetries. Then there's the tantalizing possibility of AI as a cosmic translator. The universe speaks in math, a language we've painstakingly decoded over millennia. But what if there's a dialect we haven't even recognized? Machine learning thrives on finding hidden correlations in vast datasets. Applied to the cosmos, it might detect subtle numerical patterns in the masses of particles or the spacing of galaxies, clues that our current equations are approximations of a grander theory. Some researchers speculate that advanced AI could even invent new mathematics, crafting frameworks so alien to human thought they'd be like trying to describe color to someone born blind. But the most profound role for AI might be as a bridge between scales. Our universe operates on levels from the quantum foam to galaxy superclusters, and we've long struggled to reconcile these extremes. Machine learning excels at multi-scale analysis, linking the behavior of neurons to brain function, or weather patterns to climate trends. Applied to physics, it could uncover how quantum fluctuations in the early universe seeded cosmic structures, or how black hole singularities might relate to the Big Bang. Some theories, like loop quantum gravity or holographic duality, are so computationally intense they've resisted full exploration. AI could be the key to unlocking them, simulating scenarios beyond our current computational limits. Of course, this partnership isn't without risks. An AI might derive a perfect theory of everything and express it in equations no human can comprehend. Or it could uncover truths so destabilizing they reshape our sense of reality. But these challenges pale beside the potential. For the first time in history, we have a tool that can match the universe's complexity with its own synthetic intellect. The cosmic mysteries that have eluded us for millennia, dark energy's nature, the origin of time, the reason for fine-tuning, might not just be solved, but reframed by minds unbound by biology. And in that reframing, we may discover that the universe's perfection isn't a puzzle to solve, but a conversation to join, one where silicon and stardust collaborate to read the cosmos's deepest secrets. The next era of cosmology isn't just about new discoveries, it's about rewriting the rules of reality itself. Picture this: gravitational wave observatories so sensitive they can detect the faint echoes of black hole collisions from the dawn of time, or quantum computers simulating the birth of the universe atom by atom. These aren't distant dreams. Projects like the Laser Interferometer Space Antenna, or LISA, will soon float in orbit, a trio of spacecraft weaving a 1,000,000-kilometer-wide net to catch ripples in spacetime from supermassive black holes merging billions of years ago. These cosmic tremors could reveal secrets about the universe's first seconds, hidden in frequencies no ground-based detector can hear. Meanwhile, quantum computing is poised to crack problems that have stumped physicists for generations. Imagine feeding the fine-tuning puzzle into a machine that calculates in dimensions beyond our own, testing billions of variations of physical constants in seconds to see which combinations permit life. Current supercomputers groan under the weight of such simulations, but quantum bits existing in multiple states at once could navigate this labyrinth effortlessly. They might uncover whether our universe's constants are lone rarities or inevitable outcomes of deeper mathematical truths. Then there's the James Webb Space Telescope's successors, like the proposed Habitable Worlds Observatory, designed to directly image Earth like exoplanets and analyze their atmospheres for biosignatures. Finding life elsewhere would revolutionize our understanding of cosmic fine-tuning. Is Earth's perfection a fluke, or does life emerge wherever conditions allow? Each new world discovered adds a data point to this existential equation, but the most tantalizing breakthroughs may come from unexpected places. Dark matter experiments buried deep underground, like the LUX Zeppelin detector, could finally identify these elusive particles, revealing whether they interact in ways that subtly shaped the universe's structure. Neutrino observatories, tracking these ghostly particles from distant supernova, might expose hidden symmetries in fundamental forces. Even tabletop experiments probing quantum gravity could stumble upon anomalies hinting at extra dimensions or holographic principles. Yet for every answer, new questions will arise. What if gravitational waves reveal patterns suggesting a cyclical universe, where big bangs are just one phase in an endless loop? Or if quantum simulations show that life-permitting universes are statistically inevitable in a multiverse? The deeper we dig, the more the mystery of cosmic perfection might transform not into a solved equation, but a gateway to grander enigmas. One thing's certain, the tools of tomorrow will let us see the cosmos with fresh eyes, not just as a static stage, but as a dynamic, evolving story where we're both audience and participants. The universe's perfection may not be a fixed puzzle to solve, but a conversation that grows richer with every discovery. And that's the most exciting frontier of all, not just knowing the answers, but learning how to ask better questions. If the universe is indeed a masterpiece of precision, every constant calibrated, every force balanced just so, what does that imply for us, its conscious inhabitants? This isn't just a philosophical musing, it's a call to action. A finely tuned cosmos suggests an extraordinary privilege. We're not accidental bystanders, but participants in a grand, delicate equilibrium. Think of Earth as a single note in a cosmic symphony. Our atmosphere, our biosphere, even our position in the galaxy, all exist within razor-thin margins. But with that precision comes a profound responsibility. If the universe has crafted conditions so exact, shouldn't we honor that by preserving the harmony we've been handed? Consider the ozone layer, Earth's fragile shield against ultraviolet radiation. In the 1980s, scientists discovered a gaping hole caused by human-made chemicals. The global response banning chlorofluorocarbons wasn't just environmental policy, it was cosmic stewardship. Repairing that shield meant realigning our actions with the planet's natural balance, a balance that took billions of years to perfect. Similarly, climate change isn't merely a terrestrial crisis. It's a disruption of the very conditions that allowed life to flourish in this pocket of the universe. Rising temperatures, acidifying oceans, vanishing species, these aren't isolated tragedies. They're tremors in a system that, until now, has operated with breathtaking synchronicity. Space exploration adds another layer to this ethical puzzle. As we reach beyond Earth, we carry the potential to alter other worlds, mining asteroids, terraforming Mars, even searching for extraterrestrial life. Each action ripples outward. The principle of planetary protection, which guides missions like NASA Mars rovers to avoid contaminating alien ecosystems, reflects this mindfulness. If life exists elsewhere, it likely thrives under its own set of finely tuned conditions. Introducing Earth microbes to Mars or Europa's subsurface oceans could irrevocably disrupt those balances, much like invasive species reshape terrestrial habitats. The universe's perfection isn't just a gift, it's a mirror forcing us to confront the weight of our footprint. But here's the paradox, our very ability to ponder these questions stems from the same cosmic fine-tuning we're now tasked with safeguarding. Consciousness, curiosity, the capacity to shape our environment, these traits didn't emerge in a vacuum. They're products of a universe that allows for complexity, for self-awareness. In that light, our responsibility isn't just about restraint, it's about participation. Just as the universe's constants enable stars to forge heavy elements, we're now the agents of further creation, from restoring ecosystems to seeding life beyond Earth. The question isn't whether we should act, but how to align our actions with the same meticulous care that shaped the cosmos. Perhaps the most humbling realization is this: perfection isn't static. The universe evolves, and so must our understanding of our place within it. Ancient civilizations saw celestial order as divine, immutable. Today, we recognize that order as dynamic, a dance of forces we're only beginning to comprehend. Our role isn't to passively admire the cosmos's brilliance, but to engage with it thoughtfully, ensuring that the conditions that birthed us endure for whatever or whoever comes next. The universe didn't fine-tune itself for us alone. It tuned itself for possibility, and that's the ultimate responsibility, to honor not just the perfection we've inherited, but the potential it represents. Standing beneath a star-strewn sky, it's impossible not to feel the weight of something ancient and immense pressing gently against your chest. This is more than just stargazing, it's time travel. Every photon that meets your eye has journeyed for years, centuries, even millennia across the cosmic ocean. When Galileo first pointed his telescope at Jupiter in 1610 and saw moons orbiting another world, he didn't just discover celestial bodies, he shattered humanity's cosmic isolation. That same awe still ripples through us today when the James Webb Space Telescope captures newborn galaxies dancing at the edge of time. Carl Sagan once described our planet as a pale blue dot, a single pixel in a vast cosmic photograph. Yet on that pixel, generations of thinkers have tilted their heads upward and felt the universe tilt back. Take Caroline Herschel, who in the 1700s swept comets from the sky with her homemade telescope while singing opera to the night. Or Henrietta Leavitt, whose discovery of pulsating stars became the yardstick that measured the universe's expansion. These weren't just scientists, they were cosmic poets, translating the silent music of the spheres into mathematics anyone could hear. What's remarkable isn't just their discoveries, but how those moments of revelation mirror our own. When you first grasped that the calcium in your bones and the iron in your blood were forged in stellar furnaces, something shifts. You're not just learning a fact, you're remembering your atomic ancestry. This visceral connection between the personal and the cosmic is what transforms abstract physics into profound experience. Astronomer Edwin Hubble captured it perfectly when he said, "Equipped with his 5 senses, man explores the universe and calls the adventure science." The emotional resonance of cosmic wonder isn't confined to laboratories or observatories. It's there when a child sees Saturn's rings through a backyard telescope for the first time, their breath fogging the eyepiece. It's in the hush that falls over a crowded planetarium when the lights dim and the Milky Way swirls into view. These moments share a common thread, the sudden, humbling realization that we're participants in a story far grander than our daily lives. Perhaps this is why cosmic wonder feels so much like homesickness. The universe's perfect constants and elegant laws suggest an underlying order that speaks to something deep within us. When Einstein described his cosmic religious feeling, he wasn't invoking dogma, but that ineffable sense of belonging to a reality both rational and sublime. Modern physics tells us the same atoms weave through supernova and synapses, that the same quantum rules govern quarks and quasars. We're not just observers of cosmic perfection, we're expressions of it. This isn't passive wonder, but an invitation. Every time we map dark matter's ghostly tendrils or decode the quantum vibrations of atoms, we're continuing humanity's oldest conversation, the one that began when the first human looked up and realized those points of light were more than decorations. They were questions, and in that endless dialogue between curiosity and cosmos, we find not just answers but new ways to marvel. The universe's perfection isn't a closed book, it's an unfolding story, and wonder is the compass that keeps us turning pages. The idea that the universe is perfectly fine-tuned for life carries an almost mystical allure, but not every claim about cosmic perfection stands up to scrutiny. Some argue that if gravity were even slightly stronger, stars would burn out too quickly, making life impossible. Yet this overlooks the flexibility of physics. In a hypothetical universe with stronger gravity, stars might simply form smaller and denser, adjusting their life cycles in ways we can't yet predict. The same goes for claims about the cosmological constant, the value governing the universe's expansion. While it's true that a minor tweak could prevent galaxies from forming, alternative models suggest universes with different constants might still harbor complexity, just not in ways we'd recognize. Another common myth conflates fine-tuning with intentional design. The fact that our universe's constants allow life doesn't necessarily mean they were chosen for that purpose. Imagine a puddle marveling at how perfectly its shape fits the hole it occupies, assuming the hole must have been dug just for it. This puddle fallacy, coined by Douglas Adams, reminds us that life adapts to the universe's conditions, not the other way around. Critics of fine-tuning argue that we're observing the universe from an inevitable bias, the anthropic principle, in action. Of course, the constants seem perfect. We couldn't exist to question them otherwise. Then there's the oversimplification of probability. Some proponents of fine-tuning calculate the odds of our universe's constants as astronomically low, akin to winning a cosmic lottery. But without knowing how many tickets exist, whether through a multiverse or undiscovered physics, these numbers are speculative. A deck of cards shuffled at random will always produce an outcome with equally staggering odds, yet some sequence must appear. The real question isn't whether our universe is unlikely, but whether its structure is truly unique or one possibility among many. Even the term fine-tuning itself can be misleading. It implies a tuner, a cosmic watchmaker adjusting the dials. Yet emergent phenomena, from snowflakes to galaxies, show how complexity arises from simple rules without external guidance. The universe's apparent precision might reflect deeper, self-organizing principles we're still uncovering. For instance, string theory's landscape of possible universes suggests our constants aren't fine-tuned but selected by natural processes, like evolutionary adaptation on a cosmic scale. This isn't to dismiss fine-tuning entirely, it remains one of science's deepest puzzles, but separating fact from myth requires intellectual humility. The universe's elegance isn't diminished by skepticism, it's amplified. Every debunked claim sharpens our questions, steering us toward more robust theories. Whether the answer lies in multiverses, undiscovered physics, or something stranger, the pursuit demands not just wonder, but rigor. After all, the cosmos owes us nothing, not even easy explanations. Let's play a game of cosmic what if, a chance to tweak the universe's dials and see what happens. Imagine waking up tomorrow to a world where gravity is just 10% stronger. At first, it might not sound like much, but the ripple effects would be catastrophic. Trees would struggle to grow tall, their trunks snapping under their own weight. Mountains would compress into stubbier versions of themselves, and even your morning coffee would feel heavier in your cup, but the real chaos would unfold in the cosmos. Stars, squeezed tighter by gravity's stronger grip, would burn hotter and die younger, collapsing into black holes before planets could form. Life as we know it would never get a foothold in such a crushingly intense universe. Now flip the scenario. What if dark energy, the mysterious force accelerating the universe's expansion, simply didn't exist? Without its gentle push against gravity's pull, the cosmos would have collapsed back on itself eons ago. Galaxies would never have drifted apart. Instead, they'd clumped together in a suffocating embrace, overheating in a dense, fiery soup. No vast stretches of space, no quiet corners for solar systems to evolve. Just a crowded, overheated end before life could even blink into existence. These aren't just fun thought experiments, they're stress tests for reality. Like pulling a single thread in a tapestry to see how much unravels, they reveal how tightly woven the universe's laws truly are. Take the strength of the electromagnetic force, for instance. If it were slightly weaker, atoms wouldn't hold together, and chemistry as we know it would vanish. No molecules, no DNA, no you. But if it were stronger, electrons would cling so tightly to atomic nuclei that chemical reactions would grind to a halt. Stars would fizzle out, their nuclear furnaces starved of the delicate balance needed to fuse elements. Here's where it gets even wilder. What if the universe had more than 3 spatial dimensions? We're used to length, width, and height, but theoretical physics suggests extra dimensions could exist, curled up too small for us to perceive. In a 4-dimensional world, gravity would behave differently, its strength dropping off faster with distance, making stable orbits impossible. Planets would spiral into their stars or drift away into the void. Even the structure of atoms would destabilize, rendering matter itself ephemeral. The beauty of these mental exercises isn't just in their drama, it's in their humility. They force us to confront how little wiggle room there is in the cosmic recipe. Change one ingredient and the entire cake collapses. Yet here we are, in a universe where gravity is just strong enough to shape galaxies but weak enough to let stars breathe, where dark energy's push is perfectly countered by matter's pull, where the number of dimensions and the strengths of forces align like gears in a celestial clock. So the next time you glance at the night sky, try this. Picture a universe where any one of these constants is dialed up or down. The sheer improbability of our reality becomes not just a scientific curiosity, but a visceral, almost artistic marvel. It's one thing to hear that the universe is finely tuned. It's another to feel it in your bones, one imaginative tweak at a time. One of the most beautiful things about staring up at the night sky is knowing you're never truly alone in that moment of wonder. All across the planet, people from every walk of life have stood under those same stars, feeling that same electric jolt of connection to something vast and mysterious. Like Sarah from Toronto, who wrote to us about the night she took her 5-year-old daughter camping for the first time. As they lay in their tent, her daughter suddenly gasped. She just noticed the Milky Way for the very first time. "Mama," she whispered, "it looks like someone spilled glitter glue across the sky." That raw, unfiltered moment of cosmic recognition is something no textbook could ever capture. Then there's Marcus, a retired physics teacher in New Mexico, who shared how decades of teaching quantum mechanics never dulled his sense of awe, it deepened it. He described grading papers late one night when a meteor blazed across his window, so bright it cast shadows in his kitchen. In that instant, all the equations about celestial motion became viscerally real. "For 60 years I'd known intellectually how meteors worked," he wrote, "but seeing one streak past Orion's belt while holding a red pen made me feel like a kid again, equal parts terrified and thrilled." These stories reveal something profound, that cosmic awe isn't reserved for astronomers or philosophers. Take Aisha's account from Jakarta, where light pollution usually obscures the stars. During a citywide blackout, she stepped onto her balcony to find the constellation Scorpius blazing overhead, its tail curling toward the horizon exactly as her late grandfather had described in bedtime stories. For the first time, she wrote, "I understood why he called stars the handwriting of God." The sky didn't just look different that night, it felt like a message meant just for me. What ties these experiences together isn't just wonder, but transformation. Like David, a truck driver who keeps a battered telescope in his cab, he shared how pulling over at rest stops to sketch Jupiter's moons in a notebook helped him through grief after losing his brother. "Those Galilean dots of light became my therapy," he explained. "Watching them dance around Jupiter night after night, I realized nothing truly disappears, energy just changes form. His story echoes what astronauts report after seeing Earth from space, a cognitive shift called the overview effect, where abstract concepts like planetary fragility become heart-stoppingly real. The most unexpected submission came from Ria, a software engineer who developed an app mapping local light pollution. Her moment of cosmic clarity didn't happen under open skies but in a server room. I was debugging code at 3 a.m. when I suddenly pictured Earth spinning through that blackness outside, she wrote. All our firewalls and encryption felt like sandcastles against the tide of deep time. The next day, I started volunteering at our planetarium. Her story reminds us that cosmic perspective doesn't require perfect viewing conditions, just a willingness to let the universe recalibrate your sense of scale. What makes these accounts so powerful is how they democratize awe. Whether through a child's first glimpse of constellations, a grieving man finding solace in orbital mechanics, or a programmer viscerally grasping our planetary solitude, each experience reaffirms that the universe's perfection isn't just measured in mathematical constants, it's felt in the human heart. Your stories prove that cosmic wonder isn't passive. It's an active conversation between the vast and the intimate, where every stargazer becomes both student and storyteller. So keep looking up and keep sharing what you find. Because every time someone describes the prickling sensation of infinity creeping down their spine, or the way a shooting star made their daily worries seem suddenly small, we're not just collecting anecdotes. We're weaving a living tapestry of human curiosity, one where the threads of personal experience and universal truth twist together into something stronger than either could be alone. The night sky has been humanity's first classroom, therapist, and cathedral rolled into one, and judging by your stories, its lessons are far from over. The universe's perfection isn't a destination, it's a conversation. Across centuries and disciplines, we've woven threads of physics, philosophy, and sheer wonder into a tapestry that still shimmers with unanswered questions. Think of the countless nights spent peering through telescopes, the chalkboards crammed with equations, the quiet moments when someone gazes at the stars and feels time slow to a heartbeat. This quest isn't just about solving a puzzle, it's about learning how to ask better questions. Every theory we've explored, from the razor's edge precision of physical constants to the kaleidoscope of multiverses, offers not just answers, but new layers of mystery. String theory's hidden dimensions, the holographic principle's cosmic code, even the eerie whispers of Boltzmann brains, they all point to a reality far stranger than we imagined. Yet here's the paradox: the more we uncover, the more we realize how much lies beyond the horizon. Like standing on a shore where every wave brings a new fragment of some vast, sunken city, we're piecing together a map of the unknown. But this journey does something profound to us. It reshapes how we see our place in the cosmos. When you grasp that the iron in your blood was forged in a dying star, or that the same quantum rules governing atoms also sculpt galaxies, the boundary between out there and in here dissolves. You're not just a spectator of cosmic perfection, you're an expression of it. That shift in perspective is what transforms curiosity into reverence, equations into poetry. The beauty is that this conversation has no end. New telescopes will peer deeper into the past, quantum computers will simulate realities we can't yet fathom, and AI might uncover patterns hidden in the noise of space-time. Some answers will come wrapped in math, others in moments of quiet awe, like the first time a child traces the Big Dipper with their finger and asks, "What else is up there?" So let's keep asking, let's chase the next why with the same hunger that led us this far. because the universe's perfection isn't a static fact to file away. It's a living dialogue, an endless invitation to look up and wonder. And in that wondering, we don't just discover the cosmos, we rediscover ourselves.